I'm back again and welcome to Connected Particles. For many students and for majority students, this is the hardest topic because sometimes they cannot get idea what connected particles are and in which cases you can consider those particles as connected. So in the next few minutes, we'll discover actually what connected particles are, and basically we will come back to the modeling again because you understand that this is kind of simplification, because indeed if you consider modeling in math or in physics, you come up within some simplifications, because in reality, even if the particles connected or real objects are connected, sometimes you have more complicated picture and more complicated case, so that you cannot consider them as connected particles model. All right, it's right time to reveal all those theoretical bases and physics that lies behind the scene, and also to reveal approach that we're gonna use and apply to the following problems, which are, of course, is gonna be challenging and EP and P levels. Let's get started. So first, we're going to start with approach and formula. So that's why we need to understand in which case we can consider particles as connected. All right, sometimes you might have a system of objects, and each object might be connected with each other, right? So for example, let's consider this kind of snake that consists of 4 parts, and it moves in some way. So you understand that in this case, at each moment of time or at each time instance, each part is moving in different ways. But there is one thing that you still can consider this more complicated object, like several particles connected, as connected particles model. And I'll explain why. So first of all, you understand that each particle connected with each other by some kind of string or thread or maybe a rope. And if in the case the rope is very light, so the mass of the string is very small, let's say it's much smaller than the mass of each object in the system. Let's say that's going to be object 1 with mass m1, that's going to be object 2 with mass 2, m3 and m4. So it means that for any I, which is the stays for index of mass, the mass of the string is much smaller than any mass of the part of this system. So that you can say that the string is pretty light, so that you don't need to take into account this part. All right, and the second simplification that we're going to use is that this string is inextensible. Basically, you cannot stretch this string. It keeps the size the same, it keeps the length the same. This is the same as for pendulum. Remember, if you have a pendulum that's basically can be represented by a ball which is attached to the ceiling, and you probably slightly push this and then released. Okay, so for example, you hold it, you divide it by some angle, and then you released. From this point, you understand that actually the string that is suspended by can be considered as inextensible. Otherwise, the length will be changing and it will be more complicated motion. That's the same. So we are going to consider not only the string, not only very light, but also inextensible. Inextensible means length keeps the same, length is constant. So what it means? It means that if the first object moves with some velocity u, object that follows the first one, which is in this case m4, will keep the same speed but probably different direction of the velocity. but the speed is going to be the same. So if you take absolute value or magnitude of u4, that's going to be the same as for u3. So what it means that the speed and acceleration magnitude will be the same for every single particles. However, as you can see, direction in each time, right, each time instance might be different. All right, so where it's still applicable, of course it's still applicable when you have a horizontal plane or horizontal surface and you have two objects with different masses like this. So you have probably the rope, so you apply the force, which might be in general case at some angle, right, to the horizontal plane, like alpha, and those two objects with mass m1 and m2 are connected with the light string. Let's depict the string with the red line, actually pink one. And this string is inextensible. If it's inextensible, it means if m1 has acceleration a and velocity v, in our case, m2 also will have the same parameters. In this case, direction is still the same if you apply the force, because you can consider those two connected particles, m1 and m2, as moving along the same straight line, okay? In this case, you can consider this model as connected particles model, okay? Where two objects in this system are moving along the same straight line, keeping the same kinematic parameters like acceleration and velocity the same, okay? Because the string is inextensible. If it were inextensible, of course, M2 might be lagging for a while. Then it's going to be during braking, it's going to be like falling with faster and maybe with more velocity in comparison with object 1. Okay, so you understand that that's the same as if it's rigid rod which is not compressible, so that the distance between m1 and m2 keeps the same, and every single kinematic parameter like velocity, like acceleration, and also displacement, they will have the same for both bodies within the system. However, in this case, as you understand, direction is different because each part moves in different ways. However, still the magnitude is going to be the same, right? In that case. All right, have a look here. I'll give you more examples. Let's choose, we cannot choose, all right. So let's choose inclined plane. For example, you have inclined plane here with one angle of inclination, and here is going to be another plane with another angle of inclination. For example, let it be alpha, and that's going to be beta. And they're all different. For example, alpha may be 30 degrees, while beta, let's say it's more about like 50. Okay, let it be 50 degrees. And you have two objects on it. So let's take two objects. And let's say object 1 is going to be a small box, while object 2 is going to be maybe a bigger box in mass. It's going to be M1, that's going to be M2. And how they connected? For example, there might be a small pulley that can smoothly turn, and so that they connected like this with one string that goes over that pulley. You understand there are attaching points to two objects, and that's going to be a pulley here, so that this string is, you can consider it as the whole string just going over this pulley. Or it might be, you know, a very smooth corner so that there is no friction. All right. So what can you say? Is it connected particle system or it's not? According to definition, what ALevel says, so they said that connected particles are basically a system of where all parts of the system are moving in the same straight line. However, this is not the case. It doesn't like satisfy this definition because obviously If this object moves downward along this inclined plane, while object M2 with M2 is moving this way, again, you understand that velocities will be different. However, the magnitude of the velocity, i.e. speeds, will be the same for both objects. If this string is inextensible, we still consider that this string is inextensible. However, directions will be different. Let it be V, let it be U, because of different angles, right? And you understand that M2 is moving along surface with angle of inclination alpha, and that's completely different direction. However, still can be, you still can consider those two objects, this couple, as connected particles. Why? Because actually the magnitude of speed will be equal to the magnitude of the speed of object M1, and that's for M2. And what about acceleration? So magnitude of acceleration be the same, because you consider that this string is inextensible. And of course it doesn't have any mass. So mass is very negligible. So the mass of this string is again much less than the mass of any particles within the system. So that's why it's not necessarily that two objects should be moving with the same in the same straight line. They might be moving, as in this case, over different lines and over different directions. However, there should be definitely straight lines. For example, coming back to this, you understand that there shouldn't be any circular motion, because the curvature will give and will basically provide different acceleration, which in this case is going to be tangential and centripetals. So it's more about physics. But if you consider as if each particles of the system is moving in a straight line, so you still can consider this as their connected particles model. All right, I think that's enough with the approach. So I just maybe provide a bit more examples where you can consider them as connected particles. Let's consider a pulley, and this pulley is attached to the ceiling. So it means this pulley, you cannot use this pulley in order to get gain in the force supply, right? You just basically use this pulley in order to change the direction of the force that you apply. Okay, for example, the first case that I can give you an example with the pulley might be as the following. So you have basically two objects attached to it. For example, that's going to be object 1, and this is another string with, let's say, object 2. Okay, and they have different mass, of course, M1 and M2, otherwise they will be in the balance, obviously. So they have different mass, and this string is just goes over, okay? It goes over that pulley like this way. So there is no friction. Friction in the axis of rotation is very small. Friction is small. So can you consider them as connected particles? Of course, yes, if the string is inextensible. So again, inextensible string, so you can consider them as basically connected particles. However, the direction, again, for example, let's say that M1 is greater than M2. In this case, all the system after releasing will go in this way, so that your pulley will be rotating in a clockwise direction, right? If M1 is greater than M2. Okay, you see that both objects are moving in the straight line, vertical lines, right? But in different directions. So again, velocity are different because of the directions, but in magnitude, they're the same. All right, so I think that I can give you one more example with pulley, where the pulley is using just to change directions, similar to what you can see here with inclined planes. So that's going to be case 2. And in case 2, I'll just give you a brief idea how can be done in order to just change direction. Okay, so have a look here. So you have again the pulley, which is there. So you have suspension, kind of suspension, and you have one object hanging on it on the string like this, and let's say another object is staying on the horizontal surface like that. So that's going to be object 1, that's going to be object 2. Okay, so two objects with mass m1 and mass m2, and this object is attached to the end of the string, which is again goes over the pulley and goes to another object m1. So in this case, as you understand, you just simply want to change direction of the force that you apply. For example, you apply the force due to the gravity, which is m1g, okay, and this object m1 will be going downwards, and let's say m1 is greater than m2, and there is no friction between surfaces. Okay, so no friction, that means so m1 might be actually less than m2. Anyway, our system will go in this way, in this direction, so object 2 will be moving horizontally. So that means if you wanted just to change direction of the force that you apply an only vertical force, while you actually pass this effort to object m2. That's why you can use this pulley. And again, in this case, different directions, however, because of the inextensibility of the string, you still can consider those two particles as connected particles. All right, I think that's enough in terms of what connected particles are and in terms of the approach. So I may say only that, for example, in case 1, we have two objects m2 and m1, they connected by the string, and you apply some force to the first body. Sometimes it's very helpful to consider those two objects as one single object with a mass m1 and m2. Okay, why you can do that? Because if you don't need to take into account tension force, which are obviously here, the x on each object of the system, if you don't want to consider them, just consider the whole object as, you know, two particles as the whole objects. All right, so you apply the force and this object moves to the right. Okay, but why you can do, by the way, you can apply the third Newton's law, where for every action there should be counteraction, right, or reaction, which is actually in magnitude the same, but it's opposite in direction. So that's why basically those tension force, the x on object 2 and object 1, they will be the same magnitude and opposite in direction. Actually, this outcome you can use only if the mass of the string connected them, or mass of the rod connected them, those two bodies, is negligible small. All right, only then. If you want, I'll prove why is that. You just simply can apply the second Newton's law to this rod or to this string. So ms times a is going to be resultant force. In this case, let it be this as the positive direction. So it will be T2 minus T1. All right. And because of this mass is negligible small, you'll see that this result is 0, and that means T2 equals T1. But this is again only in a case when your connection string or connection rod is negligible small. In most questions, you actually will have this. Only in more complicated questions related to mechanics, to physics, you'll see that this mass is not actually 0. Very interesting problem that I saw, I don't know, maybe a year ago. That was about the chain, which is which is put on the edge of the table, and in this case you can assume that, yeah, they're connected particles, but the problem is that because this part makes the whole chain moving down, every time you'll have change in mass of the hanging part. Like M2 and M1 and M2 every time gets increased while M1 get decreased over the motion. In this case, you still can consider as connected particles, but the problem is the mass is changing. So in this case, probably you need to take into account the mass of connecting, connecting part, which connects M1, M2, but you can skip this and consider as the whole motion because acceleration and speed will be the same magnitude for both objects M1 and M2 for both parts of this chain. But this is more complicated, it's more about physics, not just A-level mass mechanics. Alright, so I hope you got it, and in the next episode we will discuss not only just the conceptual approach, but I'll give you more formulas and maybe more examples. All right, so that's why you'll be ready for more complicated and challenging questions. However, that will be not really hard, trust me, as always. All right, so let's move to the next one. So problem 1 definitely can be solved using the idea of connected particles. Let's have a look at the conditions. So what you have here. So you have a locomotive, definitely a greater mass than a freight car, which is in front of it. And they connected with, kind of a shunt. Let's have a look. And let's set up this shunt is, basically, a connecting thread or rod. As you can see here, which always stays horizontal position means it's parallel to the railway track, where you can put the railway track over here like this. And this is going to be a loco. I just denote that the mass of the loco is great, let's say big M right here, and a small m is the mass of the freight car. In this case, this type of the car hopper, that's used for just carrying the grains and transferring grains of this sort of substances. Alright, so that's why I just put small m and big M. Okay, so what we're gonna do, they definitely connected with this rod, with this shunt, which can be in this question has a negligible mass. That means we don't take into account extensibility of this thread or shunt itself, and actually we're going to use a negligible mass. So that's why this allows us to apply the model of connected particles for two objects, the locomotive with a greater mass m and with a small mass m, the hopper itself. Okay, so because the locomotive pushed the hopper which is in front of it, and you see that permanent driving force of 500 kilonewtons applied, that means the engine of the locomotive produced this force. So that means everything accelerated with the same uniform acceleration, which is constant, 2 meters per second squared. Okay, that's acceleration. What we're gonna do, we need to set up the force that acts on each separate object, or we can consider the whole system of two bodies as the whole one object, and we can, maybe it will simplify our observation and our solution for this problem. So that's why I'll show you two ways how if you separate them and if you consider it as the whole one. So first of all, let's separate and let's consider each object in the system as the separate object, and let's have a look at the influence of the force. All right, so in other words, we are going to draw up the force body diagram or free body diagram. All right, so that's why we input x-axis as the positive direction of the motion, where you have acceleration towards the positive direction of this axis. And for hopper, which is here, a car, there is how many force acts on it. So first of all, from a shunt, due to the locomotive push that, we have a force which is here, and we set up this force as T. Okay, it's to the right, definitely, because locomotive push that. All right, so what's next? We do have the horizontal resistance of motion for the hopper, 5 kilonewtons. It's right here. It's against the motion, and we can set up F resistance 1, which is equal to 5 kilonewtons. Okay. So we do have pushing force, which is T. So you know, if you just apply this and consider shunt itself, it's going to be a tension actually, or the force of compression itself. But for the hopper, that's the force that acts from the side of locomotives through the shunt. So that's why you don't care about the left-hand side, but you imagine as if locomotive just push that. So it's kind of pushing force. Okay, so we actually finished with that one, and let's consider locomotive itself. We do have a driving force that's 500 kilonewtons. So let's set up this force right here. That's going to be driving force Fd, which is 500 kilonewtons. Okay, it's right here. It's to the right. So we do have some resistance to motion that acts on the locomotive. Is not dependent on speed, and we input Fr1. Now it's already done. Fr2 for the locomotive itself. This is resistant force against the motion. And what else? We do have the same force, which we mark as T, but the opposite side. It opposed motion because that's from the side of the hopper, as if it's some kind of resistance, okay, to the motion. That's enough, and let's set up the second Newton's law. Now we apply the second Newton's law and complete the equation. So we have for locomotive, which force acts on it. So first of all, it's going to be a driving force, F driving. Then we do have minus Fr2, resistance to the motion, and minus T is going to be equal to m times acceleration. I'm not going to plug the values until I just definitely know what to do, and I just want to figure out the whole formula first of all. For the small mass, for the hopper itself, we do have two kind of force, that tension force that pushes and resistant force R1, okay, that against the motion, and is going to be equal to small m 8 times a. So as you can see, the right side is the resultant force, which is expressed through acceleration times mass for each object, and the left side represented by, by each component of force, each component of the resultant force, which is breakdown by the forces that we draw up here, okay. How to solve? We don't care about the tension in this question, so that's why we need to kill this variable and we solve as the system of equation. Okay, I'll mark as the system of equation, and what I'm going to do, I'm going to just add, because I see t and negative t will be cancelled in this case. So in that case, we need to find resistance from there, so that's why first I'll add them up, and I'll get Fr2 minus Fr1, and because I've added them, I add in the right side, but I'll factorize acceleration from there. And what I have right now, I have an equation where I just set up with a green or maybe with a blue one, all variables that I know. Now the driving force, definitely I know Fr1, that it's against the motion, the resistance against the motion for the hopper. I know that, I know total mass, so I can figure out Fr2, which is basically the target variable in our equation. So that's why I'm just going to, right now, I'll express Fr2, and from here, I just transfer to the right side, and I'll have F driving force minus Fr1, and minus 8 times m plus vgam. So that's the final, the final result for Fr2, from where I can calculate. But for purpose of comparison, I'll just, to put it in frame in order to see what we have here. All right, so let's do it right now. For the reason of to be consistent, I'll just try to diminish this and maybe just go a little bit here because we've got that. And now the left side is our force and I need to calculate. So what I have 500 kilonewtons. So I'll use the units for the force in kilonewtons. I will write 500 minus FR1, which in our case is 5. Just take away 5 from here. And I also need to take away acceleration, which is 2 meters per second, to multiplying by the total mass. The total mass is going to be 127. So 127. So that's why finally FR2 in kilonewtons, I'll get 495. And minus 2 times 127. Okay, because I do have tons, actually. You understand that actually this part is going to be in kilonewtons because tons is simply 10 to the power 3 kgs, right? So if I use that, actually this part is going to be in kilonewtons. So that's why I'm okay with that. I'm not going to apply this cubic power of 10. So I'll just simply multiply them. And I'll get 254. 254, okay? And if I take it away, I'll just simply get 1, 4, and 2. And I'll get 241 kilonewtons, the resistant force that acts on the locomotive, all right? So I hope you got it, but for comparison, I'll show you just a bit different approach as if I consider the whole object as the single one, you know. So that's why I just move here. I have the same actually problem here, and I just combine them. By combining them into a single object, what's the purpose for that? I'll just simply exclude all internal interaction of two bodies within the system. So that means right now I have a single object that basically includes the locomotive and the hopper itself. And I'll consider only the force that acts on each part of the body, but as if I applied to the whole object. That idea will simplify our solution in that case. So what do I have? I have, of course, F resistance 1 that acts on the hopper, which is equal to 5 kilonewtons, and I do have FR2 that is unknown that acts additionally onto locomotive. That's our target one. Okay, what I have? I do have the driving force that acts to the right. And that's it. You see, there's much more, simplified version of what we've done before. So that's the easiest way. And if you don't care about any internal force that acts within the system, just you can combine them into the whole system and, basically you simplify the steps that we've done here. All right. So let's do that, and let's complete for the object m plus m, the second Newton's law. So I multiply by a, because the whole object has acceleration a to the right, and this is the positive x direction. So I'll get driving force minus Fr1 and minus Fr2, from where I can express Fr2 with no problem. It's going to be F driving force minus Fr1 and minus 8 times m plus m. This is going to be much easier and it took just 2 minutes to go through, all right? After you've got complete understanding of what's happening, all right? So, okay, we've done with that, but unfortunately, using this approach, we cannot find the answer to question B. So that's why we just come back and we use equations that we've accomplished before, because they're much more simple, and they are much more appropriate to the question B. Okay, so we care about the compression force in the shunt, but hold on, like you might ask the question, so what's the compression force? Let's consider a shunt. So if you start applying the approach that you consider shunt and thinking about, okay, you apply the third Newton's law and say, okay, instead of two forces that act on that way, on to the right and to the left, you apply the concept of the third Newton's law, that those forces are the same but acts in the opposite way. That's exactly what you have for the shunt. And you'll be right. But because the mass of this shunt is negligibly small, and if you try to complete the equation, mass of the shunt times acceleration, and you apply this approach, you just simply have the difference, you'll get zero. Why? Because actually, you use that idea, and in reality, the force will be different. For example, this force is going to be T1, this force is going to be T2. And what you will have, you'll have the difference, because the shunt is going to the right. You'll have T2 minus T1. And in general case, it's not equal to 0, but you assume that mass of the shunt is 0. So hence you can think that T1 is equal to T2. Okay, so this, the assumption that leads to the outcome, the equality of the tension force that acts on their shunt, or compression force. But how would you do that? Finally, you still didn't get the solution for that. Okay, no problem. Let's remember how we consider spring. Let's have a look here. So you have the spring suspended, and you have the load, which due to the gravity acts on this spring and basically stretch it. You understand that the single force that acts on this object is the force of elasticity. According to Hooke's law, it's proportional to the extension, right? So it's proportional to extension delta x, due to the fact that this load actually is heavy and it's, it pulls the spring down. But you ask about it again. Let's compare with what we have for the shunt right here and what we have for the spring right here. What's the compression force? In our case, we do understand that this elastic force is actually the force of the force that applied to the spring. That's why it's extended due to it. We understand that also if we consider two forces that acts on the spring itself, there are two types of force. Again, elastic force that acts, the elastic force that acts from the load downward, and the reaction force that withhold the top end of this spring. And there again, they're equal because of the spring of the mass is negligible. But the force that acts on the spring basically becomes the stretching force. In case if it's compressed, like in our case, it's going to be the force of compression, but this is the one force, the single force. So that's why if you see this analogy, you definitely can answer to the question B. So the tension force becomes the compression force in our case for the shunt. So you can choose any T you like. For example, let's take here from the second equation for the small mass of the hopper and express T. That becomes the compression force. Compression force. And we can straight calculate that. It's going to be FR1 plus, so 45 tons, right? Which in our case is MA. So we just can add to 5 kilonewtons. We can add M times A, which becomes 45 times 2, okay? This result also will give us kilonewtons, okay? So we'll get how much? 45 times 2 is 95 newtons. Sorry, kilonewtons that acts on the shunt, due to the fact that it's between the locomotive and the car, and due to the fact that the locomotive actually acts on the car and pushed it. So finally, we've got the result for the compression force, which in our case becomes 95 newtons. And that's going to be the answer to question B, okay? So that's why I just move here and say that finally the compression force, TC, becomes basically 95 kilonewtons. Okay, so I hope you got it. I hope you got it. And actually, I would like to set up the result. 241 kilonewtons. FRT, 241 kilonewtons. Okay, so I think that's the complete explanation for all, all details that might be confusing for understanding and for proper comprehension. I thought that is going to be much more than enough, and you got it. And you just simply apply this concept to whatever problem you have. In the next video, you'll see maybe more interesting problems where there will be more than two bodies, two objects connected to each other, and that's going to be interesting. And also through the connected over the pulley, when the thread is passed over the pulley. It's much more interesting questions. All right, hope you got it. Consider subscription to my channel, and don't forget to like this video and share it with others who still struggle with mechanics. See you in the next episode. Peace out. So problem 2 itself actually describes the case where there's three bodies connected with each other so that two bodies stays on the horizontal surface and moving along it, while another object is heading on the string vertically down and moves down, because definitely if you even take into account the force of friction and any resistant force to the motion, the force due to the gravity for object M1 is greater, and hence the system is moving. Otherwise it won't move, right? Okay, so that's why we need to start thinking about force body diagram or free body diagram for all three objects. That's the normal step here. Then we will set up the second Newton's law equation, okay, for each object separately, or sometimes maybe we will combine two objects M2 and M3 in a single one. If you don't care about tension force that actually exists in between them, okay? If we don't care about those forces, that will be done for convenience and for simplification. And we also need to take into account friction force through the coefficient of friction. So that's why the starting point here is to draw up all the forces, and then I'll show you how the force of friction is connected through with reaction force through the coefficient of friction, which in this case is given as mu, okay? The coefficient of friction between these bodies and the horizontal surface is mu, so you're given here, and you don't worry about that. Okay, so let's draw up all the forces, the x here, and that's why for simplicity I'll depict them with, this kind of stuff, using that purple color. So first of all, for object M1 we do have, of course, the gravity force. Don't mess up with the weight, because it's most of the time it's better to use a gravity force, okay? And in that case it will be always correct. So that's obviously that's going to be the tension force, and let's mark as T1. So this tension force also acts on the object M2. So my idea is to combine both object M3 and M2 in the single one, so we can consider as if there is a total object with the mass M3. So here is the mass M3 plus M2, where we do have tension force T1, okay? But also because we do have the friction force here, so we also apply against the motion, because actually the motion is downward with some acceleration a, and to the right, and we consider horizontal part of the connected particles. So that's why we do have friction here, and that's why the total friction is going to be F friction force that we're going to connect with normal reaction force, okay? So let's have a look. Now we're gonna set up second Newton's law equation, second Newton's law, and let's write it for object M1. due to the fact that they obviously can be considered as connected particles. As you remember the previous case, we discussed that there are two different types of straight lines. One is horizontal one and the vertical one. And we understand that this string is inextensible and it's weightless. So we are going to consider as the whole object moves with the same acceleration at given point of time. I mean, each part of this system is moving with the same acceleration and magnitude. However, acceleration in direction is going to be different, of course. All right, so for M1, we can set up M1A is going to be equal to M1G minus T1. Okay, as you understand, I've chosen the positive direction downwards. So set up this direction downwards as a positive one. So maybe it's better to say this one. So let's say that's positive y direction. And let's say positive x direction is going to be in that way. Maybe proper to set up this arrow here. And it's going to be positive x direction. As you can see, sometimes, you can use the Cartesian plane and set up the xy axis like as you normally do it for graphs, right, in algebra and math. But you can find more appropriate to use separate axes. This also works, and it doesn't matter. So in that case, I'll choose this way as the most appropriate. Okay, so for the object which basically combine two masses m2 and m3, we do have the following. So the total mass m2 plus m3 times acceleration is going to be equal to, of course, to the right, here is the tension force due to the fact that this m1 pulls all the system along the way, and minus friction force. So right now we need to find what? Find the expression for the magnitude of acceleration A and for the tension of the thread. Okay, so first of all, let's set up a friction force. As you remember, it's proportional. So this, there are two types of friction force, dynamic and static friction. So in our case, all is moving, and we can set up the proper equation for the friction force of dynamic friction force. So in that case, it's proportional to the reaction force. So that's why we can write mu times r, where r is the total force that acts upwards. Okay, so it's going to be upwards, and let it be r here. So in vertical way, there is another force, m2 and m3 times g, which is going to be gravity force. So that's why, due to the fact there are no other force, we can say that the reaction force is exactly represented by the gravity force for the combined object. So that's why the friction force in that case is going to be equal mu g in the total mass. All right, so it's done with the friction force, and now we just come back to the equation. So here we're going to add two equations in order to get rid of T, tension force. So that's why we'll get A times, so I factorize A on the left side, and that's going to be the total mass, M1, M2, and M3. Okay, and on the right side, T1 will be cancelled everywhere, and there will be M1G minus what you have here, mu g, and the total mass m2 plus m3, because instead of friction force we plugged this expression. So I just even set up the frame so that you understand how this works, and also that one. Okay, and basically we add up two equations, 1 and 2. All right, so and finally what's left is to express acceleration from here. That won't be like hard stuff. It's going to be pretty easy, and we can do the following. So what I'm going to do, I'm just going to factorize g and write that over the total mass, m1 plus m2 and plus m3 in times g. And that's going to be the resultant formula for the acceleration that each part of the system has in that case. So let's analyze. Let's assume that there is no friction. Let's just consider and provide some more, deeper analysis here. If mu is going to be 0, means no friction, no friction here, okay? We understand that we will get basically acceleration to be equal a portion where m1 represents in total mass. I'll mark a total mass of the system as m total. So that's going to be a fraction m1 to the m total, okay? As you understand here, m1 is the mass of the hanging object that actually, due to the gravity, pulls the rest part of the system. And obviously, the gravity force, it was fallen if you actually cut off this string. So if you cut off the string like here, okay, your object will be falling with acceleration g. However, due to the fact that it has the rest system, basically the carriage behind it, it's not falling freely, but it falls with acceleration proportional to, of course, acceleration of free fall with coefficient m1 to m total. Let's assume that all masses are equal. So in our case, A is going to be a 1/3, right, of the G. Pretty natural explanation for that. This is analysis as if no friction. But in case of the friction, of course, acceleration is going to be smaller because by subtracting mu times the total mass m2 and m3, you basically diminish the value of numerator and hence diminishing acceleration, total acceleration of the system. All right, so I hope you got it. That was a brief analysis. What if? What if we assume that there is no friction in the system, not only in the pulley, but in the whole system, but that with friction. This formula is given with friction, okay? Friction. Okay, and the rest part, what's left is to express tension force, but where? Find expression for the tension of the thread binding together bodies M2 and M3. So right now, of course, we need to apply the tension force. The tension force to each object. So that's why, to answer the second part of the question, I'll just move here. And now we ask about this tension in this thread, okay? Connected or binding M3 and M2. So basically, right now, we can say that because we know acceleration A, we can basically complete an equation for either for M2 or for M3. So let's complete for M3 because it would be much more convenient. Let's be tension going to be T2. So we do have still the same friction force, but in that case, friction force is going to be like kind of, let's say 3, because this friction force, F3, is going to be proportional to the reaction force for the object, for the only M3. So that's why we can put R3 over there, which of course is going to be equal to the gravity force M3G. So that's why we can write the same coefficient of friction and we times the gravity force. And that's only what amendments we need to set up for our object. So that's why we can set up the same second Newton's law for M3, providing that we do have a positive direction in that way. So the same x-axis here. And let's set up the second Newton's law. M3 times A, acceleration, is going to be equal to tension force that we're looking for and minus friction force, which in our case is going to be mu times M3 and G, from where we can find the tension force which is going to be m3, and in the brackets we'll get the sum of a and mu g in that case. If we plug expression for the acceleration, so acceleration is equal to, so one more time, m1 minus mu, the sum of m2 and m3 times g and divided by the total mass. We'll get another expression for T2 when we plug in. Okay, so just write down here and we plug this acceleration here. So that's why we can even more take out g as the common factor, and we'll be left with m1 minus mu m2 plus m3 and plus mu times the total mass, so m total. Okay, m total, where m total is this one, so that's going to be the total mass, m total mass, and we divide everything by the total denominator m1, or common denominator m1, m2, and m3. And now just what's left is to just simplify the expression. So that's why the final expression for the tension force, so mu m2 and m3 will be cancelled partially with that one, because if we start expanding the brackets, we'll cancel this part, and that's why we'll be left with the following: m3g times what will be on top is simply m1 1 minus mu. I just skip maybe some steps of simplification to save your time, and you can try to do by your own. And the total denominator or common denominator still stays the same. Okay, and that's going to be the final expression for tension force, that basically here in the thread connecting m2 and m3. So that's why it was challenge problem for A level. It's not really hard, but you know, it takes more steps and more general steps. Basically, it's based on how well you can derive the formula, okay, and how well you can solve a system of equations. So I hope everything is correct here, if I haven't messed up something, but I think it's more or less what I'm expected to have. Okay, so except for yeah, I guess plus mu. Yeah, when I factorize m1, yeah, simply we'll be left with mu m1 here, so mu m1 here. Okay, and the rest part will be cancelled, so that's why 1 plus mu. Okay, and again, as you understand, if, let's analyze a bit more, if mu is going to be equal to 0, so no friction, what will happen with the tension force? T2 is going to be equal to m3g times the coefficient m1, basically the weight or the fraction or the share which m1 is represented in the total mass. So that's why it's going to be m1 plus m2 plus m3. All right, so if there is no friction, that's going to be the result. And again, it's more or less sort of, you know, pretty obvious outcome in that case. Okay, so that's the ways you can solve this problem, and I think you should got it. You should got this technique. So if you went through problem 1, problem 2, and similar type of questions, I think you will be able to solve exam styles questions and you won't have any problems. Hope you like that. That was Daniel Dallas, and see you in the next episode. Peace out. So here's problem 3 again. It's EP level, but it consists of like several questions, so of different difficulties actually. But if you start thinking about this problem in terms of drawing the picture, you're on the right way, trust me. Alright, so let's have a look. And for first 2 questions, I think we need to draw something. So first of all, as you can see, the The model of kinetic particles can be applicable here. First of all, because there are two bodies, actually the trailer and the car, so let it be car a little bit smaller because the mass is smaller than the mass of the trailer, so that's why I will mark up as small m for the mass of the car. Okay, it's 3,100 kgs, and capital M for the trailer. So they connected with invisible, basically. It's sort of like unstretchable string, inextensible lines. So that's why we definitely can apply the model of kinetic particles. So what it means, one more time, just recap quick. So it's basically the idea where two particles connected with a string can be considered as one single object because each the distance between them is not changing, so each object is moving with the same acceleration, with the same velocity at a given moment of time, and they're moving along the straight line. Okay, so that's an idea. And inextensibility allows us to judge as we described before. Okay, so what we need to do, of course, we need to drop all the forces that act on it. And as you can see here, there is a driving force that exerts, the engine exerts, and that means it's to the right. So it's going to be a driving force here, Fd. So there is also resistant force which acts on each basically object here. Let it be F1 for the small, for the car, and here is going to be F2 against the motion for the trailer. There is also tension force. So this part, the trailer actually, the trailer pulls a little bit the car, so that's why the tension force obviously directed in that way. This is for the car, this is for the car, and for the trailer, the tension force still, like, it's the same. Of course it's the same because we do have an very light string, so that's why if we apply the second Newton's law for the string, we actually can prove that both tension force are the same. Okay, because there is no actually the right side the resultant force. If you're not sure, again, rewatch the video where I explain those basics, why we can consider like we described. Okay, so what we have also, there is nothing to do except for just set up the second Newton's law. Okay, so let's set up the second Newton's law. I'm not gonna just input directional axis, so but by default it's going to be directed to the right, and everything we need to project on that direction axis. Okay, it's x-axis in our case. We also know that acceleration of the whole system is to the right, so that's why we are also given the value, so we know that. Okay, and we also given the ratio of force F1 and F2, 2 to 3, that's resistant force. Basically, if you want, I can mark up as here resistances. Okay, so force of resistance that acts on each part of the connected particles. All right, so what I'm gonna do, I can actually consider the whole object as a single one, but for those who are not sure why you can do that, I can separate actually, I will complete the two equations for the car and for the trailer. Why? Because in the next question we need to find the tension, so that's why I think it would be valuable anyway. So for the car, what I will have the driving force, which is 80 kilonewtons. Then I take away all other force, F1, and the tension, and the result is going to be M times A according to the second Newton's law. Okay, so for the trailer, what do we have? We have only tension force, so actually it's pulled up by the car, and that's the sort of like driving force that makes this trailer moving. All right, so that's why it's tension minus only F2. That's the only force against the motion, and that's going to be M times A. Okay, different M. So this is the system of equations, And so what we can do, we need to get rid of actually tension, so that's why we add them up, and we'll get driving force minus F1 minus F2 is going to be equal to, so I'll factorize A, and on the right side I will have the total mass. So actually what you can see here, this equation allows us, we could derive this equation from the connected model as if we consider two objects as the single one, okay? So because we neglect any internal forces, like tension force in our case, and any other force that acts within the system, okay? In our case, there are only tension force, so we basically kill them and we don't consider it because we need to consider only external force with which actually our connected particles interact to, okay? So this is the straight outcome. All right, so what we can do, we need to find F1 and F2 separately. That's the first question. So what we're gonna do, we can express from the ratio F1 is going to be 2/3 of F2. So what we can do, we can plug into this equation and we can also plug all other values. But I'll just derive the general formula because, you know, there are different types of students. One of them trying to calculate immediately and plug all the values. Yes, that's the easiest way, but for more complicated problems and for the skills of formula derivation is actually kind of worse thing than for those students who actually can get the final formula, okay? So that's why I'll show you how to get the general formula for F1 and F2, and then we just plug the values. All right, so we plug instead of F1 this expression in terms of F2, and finally we'll get driving force minus A times M plus M is going to be equal to, and if we plug that, we'll get 2/3F. So actually on the left side, after expressing F1 through F2, we'll get minus 2/3 F2 and minus F2. If we combine them, we'll get negative 5/3 F2. But once we transfer to the right side, we'll get this positive, so that's why it's going to be just simply 5/3 F2 here. But I don't want to keep that, and that's why I'll just erase, and I'll express, you know, as the fraction. We've got 5/3, so it would be inversely 3/5 of this whole expression, and that's going to be the resultant value for F2. Okay, so we've got that. This is F2. Of course, I'm not going to express F1 in this like awful way, and I just simply calculate F2. Let's plug the values, so we'll get 3/5, so we'll get 87 minus acceleration 5 times the total mass, which is simply the result of that. So I'll write 300 plus 4950, okay? That's going to be the final expression in terms of values, and once we do, we'll calculate that. I hope my calculator is okay, calculates correctly. So 23,850 newtons, okay? This is the expression for F2. All right, so it's right time to say that F1 is going to be equal to 2/3, right? 2/3 of F2, and if we calculate, we'll get 15 and 900, and that's going to be F1. Of course, it should be lower because it's part of F2. Okay, so there are two resistance forces of resistance that we are asking in part A. So this is the answer to part A. So answer to A. All right, and in B, we need to find the tension in tow bar. So actually, we can use the second equation from here, and to answer B part, we just simply need to express T. So tension is going to be equal to F2 plus capital MA. So that's the final formula for that. I also probably put this as the formula as well, and that's for tension. So using again the second equation, so we can calculate tension is simply F2 2385 plus M capital MA. So it's going to be equal to 48 and 600. Okay, so that's the tension force that we ask in question B. All right, so what's happening in C? So one more time, make sure you got everything the same. If not, just write the comments why, and I'll try to explain why actually you didn't get. Probably I was mistaken, so who knows, right? There's the human factor always takes place. All right, so let's have a look at C. When the car reached a speed of 10 meters per second, the tow bar was broken. Okay, so that means the car is moving faster, right? Because the driver, the car didn't apply the brakes all the way along, so it just actually the trailer was left by its own. Okay, and the driving force for the car stays the same, so it means he didn't apply any like changes on its motion, so that's why it just moved far away. Okay, so what about because actually it has lack of tension force, actually he should feel that it accelerates. Okay, the driver should feel this as if here actually in reality he is accelerating because there is no any tension force up to the tow bar was broken. What about the trailer? The picture for the trailer is gonna be as the following. So right now it just all alone, so the tow bar, even if it's tow bar left with the trailer, it doesn't matter because it's light means it's weightless. Okay, so we don't take into account its mass, so that's why the trailer with the capital M left, and now the starting speed is 10 meter per second. So what it means its initial speed and initial velocity to the right when the trailer keeps moving by its own without any tension force applied. So now we understand because all forces of the resistance remain unchanged, so it means it's still under influence or under impact of the force of resistance. In our case, it's going to be F2. So we've calculated F2 as 48 and 600 newtons right now. And that's it. So there are no other forces. There are no driving force. It's only the force that acts on it. So there are two ways how to solve. I would use the laws of physics. So that's going to be a kind of shortcut. I'll show you two ways. So using the physics law, so using energy conservation. So you ask me what's the conservation here if the resistance force acts, but it doesn't matter. So energy is changing, of course. So change in the mechanical energy of this object is going to be equal to the work done of any other force. In our case, the work done by the force of the F2. So in other words, work done is going to be the work done by the force of resistance. So now it's slowing down, and acceleration, of course, according to second Newton's law, is directed to the left. Okay, but because we asked about the distance covered, how can it help? We can express the work done through the force times the distance. Okay, times the distance, and it's going to be negative. Why? Because actually displacement is to the right. So actually I need to make a little amendments. Of course, d is going to be equal to the distance, but in reality it should be displacement. Actually it's scalar product of the force and displacement, but according to what we see here, displacement is to the right while the force is to the left, so that means they should have negative sign. Okay, what about the change in energy? So because there is no any change in height, so it's still moving on the horizontal road, change in energy is going to be equal to change in kinetic energy. And what it means, because finally stopped, so the final kinetic energy is 0. So kinetic energy 2 minus kinetic energy 1, and this is by definition, but kinetic energy 2, so it's going to be equal to 0, and we'll be left with minus initial kinetic energy, which is mu squared, oops, in our case capital M, because that's the trailer, mu squared over 2. And if we equate that to the right side, we'll get mu squared over 2 is going to be equal to F2D. Now you understand why two signs, we actually need them, because later on they will be cancelled and everything is correct. From where we can express distance. So distance from here is going to be equal mu squared over 2 F2. So you understand that I actually put more efforts, and that's why it took a bit longer, because I explained how to apply this in details. Okay, now if you want, you can just plug the values and we can calculate. Okay, how we can calculate, so distance is going to be equal, so plug all the parameters. So mass in our case is 44950, and we just plug that, calculate, and what I've got 1038, about somewhere around 10.38 meters. Okay, that's how far it will move. Okay, until the stop. How to use the second way? Through basically kinematic approach, or maybe you apply also second Newton's law. So because you understand, acceleration is no longer be equal to 5, right, meter per second squared. Why? Because this new acceleration, and this is acceleration of the trailer itself, so obviously it should be different. So for those who were trying to apply, for example, simple formula d equals to u squared over 2a and plug a equals 5, were incorrect in this approach, because acceleration is a new one. However, you can use this formula, right, because final speed is 0, so finally d is going to be equal to u squared over 2a. Everything is positive, don't worry about that. So which acceleration we need to use? Of course, we need to figure out, and we can set up also second Newton's law, where F2 is the only force, be equal to m times a. And if you plug acceleration being equal to F2 over capital M into the formula, you'll get what you actually should get. So u squared over 2F2 and times M. Actually, as you can see, the formula is still the same as you actually expected to have. But this takes into account a bit different approach. So actually, this also works, but for me, it's easier to apply some knowledge from physics. And I also encourage you guys who also study physics, apply this way. All right, so hope you got it. So we covered the whole set of questions for this set related to connect particles. I hope that it was really helpful for you guys, and see you in the next episode. Peace out.